Okay, thanks a lot for being here, and thanks to John and Cody for the very kind and friendly invitation. So today I'm going to talk about this work, the Gravitino and the Swampland, that appear exactly today, and is in collaboration with Nicola Cribriodi from Vienna and Dieter Lust here in Munich. So before I start, a disclaimer. So our work does not directly contribute to the discussion of recent investigation about gravitino physics on the Sitter backgrounds. And with this work, I mean, in fact, the recent two works by Long and McDonough, and in fact, like Evan talked last week about this, and these other two papers that appeared very recently. So I usually like to give an outline in order to understand where we are and in order to guide the audience. And I will start with some motivation. Then I will give you the conjecture, our conjecture on the gravitino mass. Then I will discuss some tests of the gravitino mass conjecture. And then I will discuss some phenomenological implication of the gravitino mass conjecture, and finally some conclusion. So let's start with some motivation. So we don't have supersymmetry so far. And at present, given the very small dark energy density, we can have this kind of relation between the scale at which we expect supersymmetry to be restored and the gravitino mass. We don't have any definite indication, at least like theoretical indication, on expected mass range of M3 this had model dependent result. So this was our motivation, and we came up with this question. So, and the question would be, is there any fundamental property of quantum gravity that might give us information about the gravitino mass? And this reminds us of somehow of the question that usually one asks within the Swampland approach. And given the audience, and given this seminar have been around since like almost 1 year, I believe I don't have to dig into explaining what the Swampland program is. I give here some reference, but also some nice review. But of course, we can say that the Swampland program, in fact, like deals with differentiating between effective field theory that would be consistent with quantum gravity and effective field theory which wouldn't be consistent with quantum gravity. And everything expressed in terms of, in fact, like fundamental property of quantum gravity, fundamental, constraint that quantum gravity would pose on our low energy effective field theory. So we started to do like the job of a detective, as it's very common within the Swampland approach. We start to look at different effective field theory, and we came up with our conjecture that we call the gravitino mass conjecture. So let me start saying what is this. What is this conjecture, and then I will discuss implication, connection to other conjecture, and test in string theory. So the conjecture says that the limit of small gravitino mass, so M3 going to 0, always correspond to the massless limit of an infinite tower of states, and consequently to the breakdown of the effective field theory. Of course, the breakdown of effective field theory. We have the breakdown of effective field theory once we identify the quantum gravity cutoff with the species scale, but we will discuss this some slides later. So one natural consequence is that such a limit would be at infinite distance. I must say that like some weeks ago, still the name of this conjecture in our draft was the gravitino distant conjecture. Then afterwards, we changed it to gravitino mass conjecture because we realized that in our work, actually, the main character that was playing really a role was the mass, but not the fact that it was not really the distance. And it's kind of funny because we received an email this afternoon from Luis Ibanez and collaborators saying that tomorrow they would post a paper called the gravitino distant conjecture. So we really look forward to seeing that. So evidence of this connection between the infinite tower mass and M3 alpha have been also discussed in this paper, and probably surely in many other papers, but let me list this too. So in our work, we consider a generic dependence of the mass tower, that is this scaling here in terms of n, that is that we consider to be, we say that we conjecture to be order 1. In all the examples we consider actually is really order 1, and we call the for n equals to 1 the strong GMC, so the strong Gravitino mass conjecture. Of course, this formula is meant in unit of reduced Planck mass. And as I said, I mean, we consider this generic depends on the mass tower, but it's not really crucial for our conjecture. So our conjecture says that in the limit of small Gravitino mass, we get this massless tower, this infinite massless tower. So in principle, we can allow for correction to the simple scaling. And for example, these have been considered in this work, not precisely in terms of the Gravitino mass, in terms of the Susi-Elias cosmological constant, but in fact they are the same. And this in fact brings me to the next slide, that is a relation between the GMC and an anti-de Sitter distance conjecture. The anti-de Sitter distance conjecture was proposed by, in fact, Dieter, Ehrenpalti, and Kumrumbaffa around 2 years ago, and say that the limit of small ADS cosmological constant, they call lambda here, is accompanied always by a light infinite tower with mass that goes like a power law of the cosmological constant. So for Susi-Elias vacuum, where we have the relation that m squared 3/2 is equal to minus lambda divided by 3, basically the GMC, so our conjecture is basically equivalent to the ADS. So where we have to just identify n, the power of the mass scaling that we consider equal to 2 times a. Things get more interesting when we break Susi. So at the level of non-Susi-Elias vacuum, in fact, we have this general lower bound on the Gravitino mass that is always bigger than minus lambda 3/2. And in general, we can say that the GMC is different. So our conjecture is different from the ADC in terms of prediction, in terms of phenomenology, in terms of everything. However, if you look at this bound, we can say that when the mass of the Gravitino goes to 0, also the lambda should go to 0. So this means that always the GMC in area space always implies the ADC. And but the opposite is not true, of course. So we can still have a vanishing cosmological constant, for example, by tuning the supersymmetry breaking terms, and but still keeping a finite Gravitino mass. Other 2 points in which our conjecture differs drastically from the anti-de Sitter conjecture is, let me point this one, the fact that the extension in the same paper of 2019, it was given an extension, a possible extension of the ADC to the de Sitter space. So basically where we consider just the mass still related to in fact, to the cosmological constant, even for positive potential. And nowadays, this kind of extension to the de Sitter space would imply that there should be a tower with mass of this order. And if A is order 1, this could be, at least in my eyes, a bit problematic for the phenomenology. Although, of course, one could cook up some phenomenology. But we don't observe such particles, at least seems we don't observe such particles. And one should, well, keep under control this kind of tower, this kind of masses. So our conjecture does not predict this kind of things because, in fact, as I said, we can go to the limit of very small cosmological constant, but still having a finite Gravitino mass. And the second difference is that that the ADC basically does not allow any effective field theory with finite number of fields interpolating ADS, Minkowski, and yes. Instead, our conjecture in the GMC basically makes, is valid both in ADS backgrounds, Minkowski background, and yes backgrounds, because the Gravitino mass plays a fundamental role in in the three backgrounds, in fact. Let me tell you like something about the test of the GMC. So in n equals 1, d equals 4, we have that the scalar potential is given always by two positive terms, what I call like the VF and D connected to the F term and D terms. So these are supersymmetry breaking terms, as I write here. And then a negative term that is given always in terms of the Gravitino mass. It is in fact given by e to the k, where k is the scalar potential, and w, that is the superpotential. So from here, trivially follows also this bound that I already show you in the case of non-supersymmetric ADS backgrounds. And it is interesting to see that this actually looks kind of analogous to the Gucci bound, but for the Gravitino. And in fact, it's very interesting to notice that the same bound, so the same bound for the Gravitino, so the Gucci bound was derived for, following, unitary arguments, and the same things, basically the same bound can be derived following, requiring unitary propagation, and in fact, holds more generally than n equals 1 suga. And in fact, the all conjecture, I think, can be regarded as an analogous of the Gucci bound. The Gucci bound as interspace does not forbid the mass of the graviton equal to 0, but pose a limit, basically say that the mass of the graviton cannot be infinitesimally small. So the same thing happened with this conjecture. We're not saying that forbids n equal to 0, so we still allow for SUSY, for example, Minkowski backgrounds, but we say that basically once you turn on the mass of the Gravitino, this cannot be infinitesimally small. So basically, we identify the tower with the Kaluza-Klein states that for isotropic manifold scales with respect to the internal volume, with respect to the internal 6-dimensional volume like this. The Keller superpotential will depend on the volume, usually like this. So the Keller potential will be minus alpha log of V plus, and a part that is dependent on a complex structure model and the dilaton that we will not consider in this talk. And so it is important to remember this alpha here. And then the VEV of the superpotential. I say the VEV because we are considering the scale of the superpotential when we are really at the minimum of the potential. Okay? That's really the important part. Just when we are really at the minimum, we can consider how superpotential scales with respect to the volume. And also in this case, we have another parameter that we call beta, and alpha and beta will be important for us. In fact, we see that if we have this two form of Keller potential and superpotential, the mass of the Gravitino will be always like this, so it will be a scaling of 1 over volume times this power here. And so remembering that we have considered this relation, this dependence of the mass with respect to the Gravitino mass as a power law, as a scaling like this, we can, once we have alpha and beta, we can find basically n. That is, n again is the parameter of the conjecture, as I said before, that we conjecture to be order 1. So let's start with the examples. In a sitter, so for backgrounds like this, LESD times SD prime, we have always that n is equal to 1. This was also considered for in the anti-de Sitter distance conjecture. But now we can consider also supersymmetric type 2B ADS vacua, for example, the KKT type. And here, basically, we have that the Keller is minus 2 times log the volume. And the superpotential, again, just at the minimum, just when really, I know the superpotential does not read like this usually. There is like a flux part plus a non-perturbative part, but when really like you consider like how this scales at the minimum, it will scale like this. And this means basically that alpha is equal to 2, you see here in front of the log, beta is equal to 4/3, and n in this case will be equal to 2. But there is like some, we have to note something, that the isotropic scaling was, it was noted in this work that isotropic scaling of the KK mass is not valid, especially for, due to this non-perturbative correction and the very small value of W0 that is required in KKT models. So basically, this implies that one receives log correction in the CC, and consequently, because we are in supersymmetric ADS backgrounds, we receive also correction in the scaling, how the mass tower scales with respect to the Gravitino mass, and we have a change in n. It's not anymore 2, but we have 1/3. We have also considered non-SUSY, non-supersymmetric type to be ADS vacuum, like the one of large volume scenario. In this case, as you know, large volume scenario consider the contribution both of the perturbability correction in the Keller potential and both the contribution in the superpotential, no perturbability contribution, the superpotential. W naught differently from PKLT in this case can be order 1. And basically we have that alpha is equal to 2 in this case, beta is equal to 0 because a leading order does not depend on the volume. And we have again an n of order 1 that is 2/3 in this case. So we see actually that the log correction actually enters how the Kege mass depends on the CC. So entering the depends of the CC, but we don't see any correction in the mass of the Gravitino, and this could be related to the fact that well, first of all, we have a non-SUSY ADS background, and also to the fact that W naught is order 1. So we consider ADS, but we consider also Minkowski, and in the case of Minkowski, we consider no-scale models of this type. And for heterotic string compactification, we have basically that n is equal to 4/3. For type 2b, GKP, or antifold, we have that n is equal to 2/3. So as you see here, is always order 1. In the paper that we are today, we consider also Schwartz model and no-scale models with F term and D term, where we see a very nice connection between the mass of the Gravitino and the gauge coupling of the Gravitino. But for the sake of not spending too much time on this example, I decided not to show you this. Instead, I will go to the de Sitter case, well, we have conjecture that our conjecture, we conjecture that the GMC should be valid also for de Sitter. However, in the paper, we provide a very simple argument that shows that actually the GMC in de Sitter, at least for the de Sitter construction that are most studied in literature, like the Gegel-Thiel and LBS and others, like the one that I said here by Westphal. Yeah, we see that here, I mean, like the GMC in de Sitter can be also supported by its validity anti-de Sitter space. And this is basically a very simple argument, basically that some of the best construction have the structure like this, so that basically you get the S by an uplifting part. If the uplifting part goes like negative power of the volume, we basically show that, but it was of course already known that the shift in the minimum of the ADS with respect to the minimum of the DS is very, very small. And in this case, basically the mass of the Gravitino, which depends on the volume, does not change much. So this means that basically the consequence of the GMC in de Sitter directly follow from the discussion of the GMC in anti-de Sitter. So then I have a last slide about n equals 2, and the n equals 2 case is is quite involved, and we have like many pages in our paper. Here actually I condense in one slide, and it's very interesting because while in n equals 1 we have no direct relation between m3 alpha and g3 alpha, where g3 alpha is the gauge coupling. In n equals 2, it is possible to demonstrate, and we do it in the paper. We are not aware actually if this was already shown in the literature. Could be, but we show basically that that there is a relation between the gauge coupling and the Gravitino mass matrix in this case, because we have 2 spin 3 half Gravitini. So this is the content of the n equals 2k theory. So, and let me give you just this simple slide. So we found actually a relation between the Gravitino mass and the Gravitino gauge coupling. So where the Gravitino gauge coupling is equal to e to the k, where k is again the Keller potential, And a function of is a model dependent function. This f, this curly f, is a model dependent function of the scalar field, where z and q are the scalar field of the vector and upper multiplets. And if you remember, e to the k is scale like the volume, like negative power of the volume. So it will go to 0 whenever the volume goes to infinity. So this was the reason why we consider the limit of vanishing mass for the Gravitino. So this means basically that the limit of G3 alpha going to 0 implies always in n equals 2 that the mass also goes to 0, and so we have restoration of global symmetry in the same limit. So it's very nice, I think, to see that in n equals 2, our conjecture is really related to the no global symmetry conjecture. In the paper, we provide also an explicit example of the ST model with the scalar potential, and here I'll give you like the expression for the mass metrics, and you see that basically the mass metrics is always equal to, I mean, depends on as a factor on G3 alpha, and so in this case, in this specific case, we can say that really like not just that when G goes to 0, also M goes to 0, but also that when M goes to 0, also G goes to 0. So it's one-to-one correspondence. So let me give you the phenomenological implication of the conjecture. Just check that I'm on time. And in order to discuss the phenomenological implication of the conjecture, we would like to first remind a couple of things. So if the mass of the infinite tower goes to 0, what we have is that if we identify the quantum gravity cutoff with the species scale, basically we have also that the species scale and the quantum gravity cutoff decrease. And so this can give us like very important constraint on phenomenology whenever we assume that the typical scale should be lower than the cutoff, as it, for example, is in the sitter. So we identify lambda qg, that is the quantum gravity cutoff, with the species scale, that is m Planck divided by square root of n, where n is the number of states below the cutoff. That's important. In fact, like if we consider that the states are equally spaced, as it is the case for kk or 1D modes, we have basically that n can be written like the cutoff divided by m. And I remind you that m is the mass of the infinite tower that we are considering to be like a power law of M3 alpha. And here in this formula here, I reinstated again in an explicit way the mass Planck, or I use mass Planck because it's more convenient for our phenomenological discussion. So if you put like these three formulas together, you can express the quantum gravity cutoff in terms of the mass of the Gravitino. So you see that basically really the mass of the Gravitino, a consequence of this conjecture is that the mass of the Gravitino sets really the scale at which, above which gravity becomes strongly coupled. And there is a parameter here still, the n that we saw here in the mass of the formula still enters also the quantum gravity cutoff. And it is possible also to write down, thanks to these three formulas that I showed you before, the max of the Gravitino in terms of the number of states that have mass under the cutoff. And this is the formula here. And basically we see that for n smaller than 3, M3 up is always lower than the cutoff. And so for n equals to 3, basically the M3 alpha is of the order of the cutoff. And so we interpret this fact with the fact that when n is bigger or equal to 3, we have no effective field theory of supersymmetry breaking. As you see here on the right hand side, we see here that we have for the strong GMC that is n equals to 1. We have in fact that M3 alpha it is lower than the cutoff. In the case of a charged Gravitino, if we assume what the magnetic with gravity conjecture imposes, so that the lambda qg should be lower than G3 half and Planck. And then here in this expression here, we use, here in lambda QG, we use the expression that we found just the slides before, that is the expression that cuts off in terms of the mass of the Gravitino. Basically, we get this first relation here. And if we assume that n is smaller than 3, as it would be in the case that we assume validity of the effective field theory of Susy breaking, as I showed you before, basically, and also, okay, the G3 alpha is smaller than 1, but this is usually the things that it is assumed within the microgravity conjecture. I mean, we get basically this form that is of the form suggested by the electric weak gravity conjecture. So now let me consider the implication of our conjecture for quasi de Sitter space. So I said quasi de Sitter space because really it can be applied to inflation, to quintessence on other, I mean, to other scenarios where we don't have like a perfect Sitter space, but we have like a slow variation of the Sitter phase. However, I must say that although we call quasi de Sitter phase, in the end, like the strongest application are really for inflation. So in general, a perturbative control of our effective field theory of de Sitter requires that the lambda QG should be bigger than H. And if we use again for lambda QG the expression that we found before of lambda QG in terms of the Gravitino mass, we get a lower bound on the Gravitino mass, and is a model-independent lower bound in terms of the Hubble parameter. So it's very useful for studying phenomenology. For n equal to 3, sorry, we see that explicit dependence from M Planck drops. We recover this relation, M3F bigger than H, that was discussed, in fact, last week by Eman, and was found, I mean, studying catastrophic Gravitino production, but also was found, I mean, almost 20 years ago by Kaluza and Linde, studying the volume destabilization in KKLT. But we should say that, I mean, for n equal to 3, we recover this, but the reason of this, of recovering this relation is very, very different from the reason why, I mean, like the reason behind this, this relation is very different from the KKLT, from what happens in KKLT, or for what happens like studying Gravitino production. And so we recover this, so we see that the explicit dependence of M Planck drops. But we should also say that, as we said before, that for the same value, n equals to 3, we don't have any effective field theory of Susy breaking. In the Zorol approximation, we have always, and so here this slide is basically focused on inflation, and it's one of my last slides. In the Zorol approximation, we have that H can be always written in terms of the tensor to scalar ratio. So the tensor to scalar ratio is that that observable that we would hope to detect. So I mean, like we would hope to through like a detection of primordial gravitational waves, and in fact, like would give us like an estimate of primordial gravitational waves generated during inflation. And currently, there are several experiments that are looking, I mean, that have target, that they have as target tensor to scalar ratio in the order of, I mean, next generation experiment have a target of around 10 to the minus 3. So by using this relation here and using the bound that we found before, so the model-dependent upper bound that I repeat here in terms of the Hubble parameter, we just replace H with this expression here, and we see that we get an expression of the mass of the Gravitino with respect to R, the tensor to scalar ratio, and it should be clear that all these quantity are at the time when the scales that today we see in the CMB exit horizon 60 e-folding before the end of inflation. So it's quite useful, this lower bound on the Gravitino mass in terms of the tensor to scalar ratio. And here there is a plot that actually does not appear in our paper, but I just did it like yesterday, and I thought that it's kind of useful. So this is a log-log plot because we are dealing with very, very big numbers. So the different lines, let's say horizontal, almost horizontal lines, are for different value of n, as you say here. Again, n is the power for the mass scaling that we are considering. So the strong GMC for n equals to 1 is the orange line here, and it's a plot of the M3 half in GV in terms, so with respect to R. So this vertical lines here, red lines, is in fact denote the upper bound set by Planck, and this vertical green line here basically is the future target of next generation CMB experiments, such as CMBS4 or this Simon's Observatory. So I find it very interesting that basically, I mean, our claim is basically that, for example, in the case of n equals to 1, that's focused on this orange line, any detection of B modes would point at a lower bound of 10 GeV that is much higher than I think that the usual lower bound that one gives, assuming Susie bragging Susie bragging at order TV, because we didn't observe the TV. I think it's like milli electron volt, the lower bound we have. And okay, it's a bit extreme. Here we go a bit extreme because this is just like an upper bound. I just say that the eventuality of detection of the highest compatible R basically would mean really like a lower bound on the gravitino mass of 10 to this 2 TeV. So in a quasi de Sitter phase, so this was like a lower bound on M3 half. So now let me tell you as a next implication, an upper bound on a scalar field displacement. So if we imagine that our theory of quasi de Sitter is sustained by scalar field displacement, so by the potential of a scalar field where we have like a scalar field displacement, we know that the Swampland distance conjecture predicts that also the quantum gravity cutoff should be lowered by this I mean, it's just an effect of the infinite mass of the infinite states with very low mass predicted by the Swampland distance conjecture. So basically, by using this and the fact that this lambda naught is always smaller than the M Planck, we get this universal upper bound on delta phi. It's just like you find like in many papers. It's just really like universal of the predicted by the STC. And now, if you replace in lambda QG again the expression for the lambda QG that we find in our paper, you see that basically we can express the lambda the delta phi in terms of the gravitino mass. And well, as an extreme, let's say, conclusion, we see that when we take n and lambda order 1, so here we're taking really 1, we see that this bound constrain large field scalar field variation. But this means like for me like really like delta phi bigger than 1, just for very high values of the gravitino mass, very close to the Planck scale, so 10 to the minus 2 M Planck. And I think this is my last slide before conclusion. We would like also to say something when the gravitino is charged. So when we gravitino is charged, Montero, Van Riet, and Vengen have shown that there is a quite general lower bound on the mass impact of a charged particle in de Sitter space. So in the case of the gravitino, this bound would read like this. So now if we use the expression, the upper bound on the gravitino mass in terms of the gauge coupling that we found just some slides before, and take like n equals to 1, so that for the strong GMC, we see basically that we have a relation between the gauge coupling and H. So this is a bound that is stronger than the one that we obtain like naively from the magnetic gravity conjecture, because we would have like H smaller than G3 of M Planck. Here we have like if G is smaller than 1, we have like a power 5 here. So this means basically that, again, detection of the modes in the next generation experiment would point at a lower bound for the gauge coupling of 0.08. Now, let me go to the conclusion. We're almost there. So the conclusion, so recap, we do a recap, and we say that we have proposed a Gravitino mass conjecture, stating that the limit of small Gravitino mass, M3 half, going to 0 corresponds to the massless limit of an infinite tower of state and the breakdown of the effective field theory. And in this work, in the paper that appeared today on Archive, we focus mainly on a scaling like this of the mass tower. I remind you that we discussed differences and similarities of the Gravitino mass conjecture and the ADS distance conjecture. I show you, we've tested the GMC in a number of examples of string compactification to D equals 4. And we have, so in ADS, in different backgrounds. So in ADS, Minkowski and de Sitter. And also I should add that we tested also in N equals 1 and N equals 2. And specifically in N equals 2, something that I forgot to write in the conclusion, really we find a connection between M and G, so between the mass of the Gravitino and the gauge coupling of the Gravitino, that allow us to connect our conjecture to the global symmetry conjecture. And finally, we have derived Fino implication in quasi de Sitter backgrounds, and especially for inflation. I think that the most interesting bound is the one that I show here, as a future benchmark of next generation CMB experiments such as CMB4 or the Simons Observatory. And then with this, that's all. Thank you.
Let us all thank Marco with our emojis for his very nice talk. There's already a few questions/comments in the chat, so let's get to those. Arena?
Yeah, thank you, Marco, for the talk. Yeah, I have a question. So in the case of N equals 1, beyond examples, do you have any general motivation for the conjecture, not in addition to the relation to the ADS distance conjecture? Or, I mean, are you at least able to define some distance in some space of field configurations that relates directly to the Gravitino mass without talking of the cosmological constant, so that you can argue for the tower or something?
I'm not very sure I understood your question. So you're saying like beyond, I mean, like beside the example we make, right? This is your question.
Examples, like some general argument beyond, I mean, why?
Of course, like the examples are very, I mean, for us, were very, very important. I mean, for us, were very important, the examples that we noticed. And in fact, I think was motivated, I mean, first of all, by example, and secondly, by the fact that that ADS distance conjecture is very strong in the case, I mean, of positive cosmological constant. Anytime we break supersymmetry, it's very strong. I mean, relates really like, so in general, like, we don't expect in supergravity. I mean, like, if you want like to say that the GMC and the ADC are like equal to each other, you should pose a relation between the Gravitino mass and the CC, basically always. So not just in the case of SUSY ADS, but really always. I mean, like in any case, independently of SUSY, if SUSY is broken or not. And we didn't see any good motivation for doing that. Actually, we discussed in the paper in the conclusion this possibility that the Gravitino mass is, is related to the cosmological constant. I mean, of course, like in the case of the ADC, is equal to, the power would be equal to 1/2. We just take it more generally. But even in that case, we see that. I'm not sure actually if I'm answering precisely your
I mean, I think it's interesting the possibility that restoring supersymmetries at infinite distance. I'm wondering, I mean, you are claiming that there should be an infinite tower of the states getting light, but I don't understand if there is any, I mean, where the infinite distance is coming from. What is the metric that you use to define the distance, or why you think that there should be an infinite tower? What is the motivation for that? beyond the relation to the ADS distance conjecture, like whether you have in mind some other.
Okay, but you're taking the implication. There is an infinite tower. We have infinite distance, right? So that it's okay. It's okay. But that's why we say that it would be a natural consequence. We didn't conjecture that it's an infinite distance, but we say like it would be a natural consequence with what we see like in the paper of the ADS distance conjecture. That actually, I mean, like an infinite tower like correspond to an infinite distance. But in fact, in the paper, we never talk about the infinite distance, and it's not really crucial for our discussion. The only crucial thing is the fact that the gravitino mass, when it goes to 0, brings down also the mass of an infinite tower. And well, for us, the example were very important in order to, I mean, I think it's like within the Swampland program, that's what people do, right? I mean, they look at examples and then like they start like thinking about conjecture.
Okay.
I believe Michaela has a comment.
Hi, Marco.
Hi, Michele.
No, it is a small comment just on the fact that this bound on the gravitino mass, so strictly speaking, applies only during a phase, right? Because
yes.
You are, I mean, it would apply today only if the Kähler potential and the superpotential could not hold from inflation to today.
Yeah, in fact, like I forgot in the talk, but we didn't forget in the paper to specify that, of course, like an important assumption of this is that the mass of the gravitino does not change much from the time.
No, especially if you want to use it for giving a hint to experiments, I guess that.
Of course. I agree. An important assumption of this derivation is that we assume that the mass of the gravitino does not change much from the time of inflation to now. I mean, in the paper also we specify that, for example, like if we consider uplift of the type we consider, I mean, like without going like to the microscopic description of the uplift, like anti-brane or whatever. I mean, like just an uplift that goes like at the level of the scalar potential that appears like a negative power of the volume. Usually, and you assume that yes, the mass of gravitino, I mean, like depends on the volume. I mean, this kind of simple scaling basically makes that basically the mass of gravitino really doesn't change really much from the time of inflation to now. I mean, like I know. I mean, there are also more involved models. I'm aware of this, and we specify this in the paper that this is an important assumption. If we assume this is an important assumption. Actually, the same assumption was made by Evan last week on this. So what they found, for example, is a bound of M3 with respect to h at the end of inflation, and they assume that the gravitino mass does not change during inflation.
Right.
Okay. Of course, the time that I'm considering is longer.
Okay, I believe the next question is by Yinan.
Hi, I just have a question on the number of species you mentioned in the scaling discussion. So do you have a general feeling or bounds on the number of species, like a lower or upper bound on this number n for your purpose, like a light gravitino or something?
So let me understand. Let me see if I understood well your question. So you are asking me if I have like any lower bound on this number n.
Yeah, some bounds like that. I think
we don't have any. No, we don't have any lower bound. I mean, all the example that we studied, I would say like n was order 1. Well, we noticed actually that we don't go lower than 2/3, but we didn't want to, to go far too much and conjecture that the lower bound is 2/3. So also because we don't have like so much meat for that. So we don't have any lower bound.
Why is 2/3? And it's a big n, it's the number of species. So
the number of species. Sorry, I thought that we were talking about
the small. It's not a small n. Sorry, it's big n. Sorry.
So you're asking me if there is like a lower bound on the. Well, I think that one could relate. Yes, it's a good question because the number, so the mass of the Gravitino would be equal to m Planck divided by n to some powers. So probably like any bound that we have on the number of Gravitino, a lower bound that we have on the number of Gravitino, on the mass of the Gravitino mass can be yes, translated into a bound on the number of species. It's actually a very interesting question because yes, it would tell us that in our effective field theory, or whatever effective field theory coming from quantum gravity, we should think about that there are this number of light species. I mean, that are below the cutoff and could generate some effects. Yeah, I agree. Thanks.
Okay.
Okay, I believe that Ivano had his hand up first. Is that?
Yes, no, wait. I think Arthur had.
Okay, Arthur
first. Yes. Okay, thank you. I have only a very brief question. I was confused by your slide on KKLT, because there W is in fact not only small due to the or large to the prefactor T, but there's an exponential suppression, e to the minus T, right?
Mm-hmm.
So W is extremely small, and the Gravitino mass is extremely small. If you allow for fine tuning, it is parametrically, I mean, exponentially smaller than the cutoff scale. So it seems to invalidate, it seems to present a counterexample of your conjecture, at least if you take seriously the discrete vacuum of the landscape. And I'm not talking about uplift, I'm talking about KKLT ADS vacuum.
I know. But in general, like, yes, thanks, Arthur. No, I mean, because we received also this question like by email, and we thought about it. But in fact, I think that in KKLT, I mean, nothing prevents from having a not so small mass of the Gravitino, right? I mean, like this, like apart from like don't consider our work. I mean.
It's not a question of numbers, it's a question of parametrics. Your cutoff goes down to the extent that the T becomes large, but the Gravitino mass becomes small exponentially in T. Your formula, I mean, I could go back to your slide, but it's not necessary because the slide was so simple. It's e to the minus T. It is very different. It is exponentially small in 1 over the cutoff.
Yeah.
Look, the cutoff goes down, the KK scale comes down as the volume becomes large with some power, okay? We agree.
Yes.
Volume large, KK scale small, some power. The Gravitino mass is exponentially small in that cutoff, inverse.
Yeah, I should think more about it. I should think more about it. But yeah, my understanding was that at the point where we have I mean, if you consider really the depth of the superpotential, I mean, we don't have any more what you're saying. But probably like I should look at it.
You can show the slide. Yeah. It was there on your slide. You simply disregarded the e to the minus T factor. Can you go back to the slide?
Yes. Oops.
Here, that was.
Yeah, sure. Just because I have also the other. Yeah. I'm aware of what you're saying. Yes, of this.
Yes.
I'm not sure if. Yes, in this moment, like I'm a bit. Yes, I don't have like a ready answer to this. I'm not sure like if one of my collaborators have like a better answer than this. I'm a bit confused right now, in fact. But okay, I will.
Okay, good. Thank you.
Yeah. Thanks, Arthur. And this is a good point. Thanks. In principle, like as I said, I mean, when we received your email, I just thought, well, beside our work, I mean, in general, like I don't know that the mass of the Gravitino in KKLT should be small. So, but okay, let me think, and I will give you an answer. Thanks.
It depends on the ability to fine-tune W0 to a small number. So some people believe it cannot be done, but then there is recent work by Demetrius, McAllister, Moritz, and Kim, which give an example, and there is, of course, a fine-tuning argument by Denef and Douglas.
Right.
So the argument that you have to make, I think, to avoid a contradiction is to say that W0 can never be tuned small, which is a strong thing to claim. I mean, maybe it's true, but not obvious.
Okay. I will think a bit more about it. But yes, the way we are considering like the limit of small of vanishing gravitational mass is not through W, but it's through e to the K. Okay, this is like an important point in our paper. But of course, you're right that this could like be a counterexample, but and it deserves like more attention. But yeah, thanks. I will think about it.
Sorry, by the way, this is true also in large volume, not just in KKT. You can play with the string coupling that in that case and decouple the Gravitino mass from the KK scale.
But Michele, in that case, if you play with a small string coupling, then you get a tower of light strings, which is parametrically some power of the light Gravitino mass. You see, in KKT is different because there it's exponential. If you take GS small, some different tower, namely the tower of light strings becomes light.
No, but if you get W exponentially small by using some exponential, which is e to the minus the d.
Oh, I see. No, but in but in LBS you do not get exponentially small W in GS.
No, I was saying in KKT. In KKT you get an exponentially small W by some non-perturbative effect in the dilaton is the same thing.
Sorry, in LVS, W is not parametrically small, not exponentially
No, I was
small.
saying that in KKT. So in KKT, you have W that is extremely small because it is controlled by some instanton.
Right.
Then you are also you can think of playing with the string coupling there as well.
Yes, but it has to be in the exponent, and it is in the parameterization in which it's given here is not in the exponent.
I agree.
Okay, thank you. Yeah, no, I agree with you.
Okay, perhaps we should move on to Ivana. I believe there's
thanks.
Zero and Dieter.
I'll try to be brief, but actually my question relates to the later part of this discussion you just had about the light strings Arthur mentioned. Namely, I wanted to know if you had envisioned any situation in which the light tower that goes, the tower that goes light as the Gravitino goes light could be something other than the KK tower, for example, emergent strings. Because usually, as far as I know, what happens is, the Gravitino scale is usually tied closely to the KK scale in most examples. Right.
So thanks for the question. Yes, in fact, usually these are the two situations we see, right? In within the Swampland, either like a KK tower or a string tower. But in this case, I mean, we didn't analyze the case. I mean, we just analyzed the case of the KK tower. I mean, all the examples we see are related to the KK tower, but it could be that that other limits probably like in other limits we don't see like a KK tower. The mass of the KK tower going down, but maybe some other things, some other effects. Yeah, so we didn't look at this. So we identify, like just like the KK tower.
Thank you.
Takahiro.
Hi, Marco.
Hi, Takahiro.
Do you think that inflation models with stabilizer field are excluded?
The difficulty I see in addressing any supergravity model of inflation like this is that I should have like really a string embeddings before talking because here like we're talking, whenever like you give me like a Keller potential, if I don't know how the field inside the Keller potential is related to the volume, it becomes difficult for me like to regard this as an example, So if I don't know like how it scales with the volume of compactification, so that's why I don't immediately see any connection well, if you give me like an explicit string embedding of this model of inflation with nilpotent superfield, well, I could talk about
not necessarily nilpotent.
Not necessarily nilpotent. So what was your? I thought that you were talking nilpotent.
So my point is that in the case of inflation models with stabilizer field, during the inflation, the stabilizer field is the field value vanishes, and that means the Gravitino mass during the inflation is basically zero. Maybe have some corrections, small corrections by maybe bending trajectory of inflation, or maybe another contribution from.
Okay,
sector.
if you take like if you take our conjecture front face like this, and you take your yes, the model where you can of course like seeing when the Gravitino mass goes to vanishing values. Yes, of course you can apply the conjecture even if you don't have like a macroscopic embedding. But I don't remember precisely. Well, these are like stuff that I studied like during my PhD. I don't remember precisely how the mass of the Gravitino goes in models with subdivided fields. So yeah, it's an interesting point. Yes, in fact. So even if, as you say, like even if you don't see any macroscopic, you don't consider any microscopic embeddings. Yes, in fact, you could talk about like the limit of m that goes to 0. Yeah. Okay. Thanks. It's a good point. I don't know. I didn't think about it.
Thank you.
You're welcome.
Okay.
Thanks.
Now that we're it's basically 10, we should cut it off after Dieter's comment on Irene's question.
Yes, thank you. I'd like to comment, in fact, on Irene's question, namely about whether there is also a distance in field space related to this conjecture. And in fact, I do believe that there is. Therefore, we also thought about calling the conjecture the Gravitino distance conjecture, but finally we called it the mass conjecture. Actually, first of all, I mean, this is also what I argued in a different paper. I believe quite in general that if there's a tower of states which becomes massless, there should be always an associated distance. But of course, this is not a very much proven statement. Let me give you a few examples why there should be a distance also connected here. I think the strongest argument is from the ADC, from the anti-distance conjecture, because we know situations where the Gravitino conjecture is equivalent to the anti-de Sitter conjecture, and for the anti-de Sitter conjecture, one can identify distance in the field space of metrics. Then, as Marco was explaining, generically there's a tower of KK states, and KK states are also clearly related to a distance in field space. And finally, I think also this fact that in n equals 2, the Gravitino mass is related to a billion gauge coupling also provides another evidence for distance, because the limit of vanishing gauge coupling I think is also very often related to an infinite distance in field space. The gauge coupling generically is also related to the string coupling, and if the gauge coupling is 0, so that's not in this case a KK tower, the string coupling could be sent to 0, and then we have the limit where you have intentional string, where you have an emergent string picture. So I think in many instances, I think there's good evidence that the limit of M3½ also belongs really to a distance in field space with a good metric where you can measure the distance with, but of course it's not proven yet. And in fact, Marco was mentioning this paper by the Spanish group, Luis Ibanez et al. I think they call it, in fact, the Gravitino distance conjecture. That's what Luis Ibanez told us today, and I'm very curious to see how they make even possibly the connection to the distance perhaps even more close. So that's my comment. It's not a question, of course.
Yeah.
Great. Well, with that, let us all thank Marco again. We managed to fill our time. I'm very happy. Thanks everyone for coming. We'll see you next week. Thank you, Marco, again.
Thank you, John. Thank you, Cody, and thanks to everyone.